This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
The global build-out of space infrastructure is accelerating, but the current trajectory is about to hit a physical wall. Modern satellites are strictly limited by their ability to dissipate heat. Because a vacuum provides no medium for convection, a spacecraft's potential power and compute capacity are capped by the efficiency of its thermal hull. Current engineering attempts to manage this through component-level design, treating processors, batteries, and radiators as isolated units rather than a single thermodynamic system. This fragmented approach results in higher production costs and lower orbital capabilities. It prevents the high-density scaling required for complex space operations. Because this thermal paradox remains unresolved, the underlying infrastructure for high-performance space computation and energy distribution has not yet been established. ScrollCiv shifts the focus from isolated components to a unified, system-level optimization framework. This framework is built on Digital Fabrica Theory, a mathematical substrate designed to model infrastructure as a continuous field. This architecture couples energy, compute, and mobility into a unified system governed by strict thermal boundary lines. By integrating these fields, the mathematics treats thermal limits as an optimization leverage point rather than a fixed physical cap. Solving the physics of field-coupled optimization allows for significantly higher power and compute densities within the same satellite mass profiles. The commercial interface for this technology is GILC Space Systems, or GSS. The first module in the GSS product stack is the Thermal Intelligence System. It utilizes fractal radiative field structures to maximize radiative efficiency per unit of mass. This works in tandem with the Payload efficiency engine. This module continuously balances compute, mass, and power loads to maintain stability and prevent thermal trucking during high-performance cycles. These configurations are validated in TwinGrid, a digital twin environment that simulates thermal and payload behavior in a virtual orbital environment before launch. The combined GSS stack provides 20 to 50% efficiency gains without adding mass to the spacecraft. Beyond technical performance, establishing an infrastructure layer requires a standard for deployment authority and industry trust. GSS provides this through the Invariant Signature Standard, or ISS. The ISS is designed to move from a specialized tool to a mandatory compliance standard. No valid signature, no deployment. GSS utilizes a revenue-first doctrine to fund this expansion and avoid premature capital dependency. The initial market wedge consists of free system efficiency audits that identify critical hardware bottlenecks for satellite operators. These audits serve as a direct conversion tool into initial optimization contracts and long-term SaaS subscriptions. This pipeline targets 3 high-growth segments: commercial satellite startups, national space agencies, and prime defense programs. The cash flow from these consulting audits is immediately reinvested into the development of the automated TwinGrid platform. Generating early revenue through high-value consulting validates the market demand and reduces the execution risk for institutional investors. The architecture transitions from a software platform to a physical presence in space within the next 18 months. This phase centers on the launch of the first orbital node. This small sat operates within a 15 to 30 kilogram footprint, serving as a physical testbed for the entire GSS stack. The node is designed as the minimum viable cell of a physical, invariant-governed fabric. Its primary mission is to demonstrate stable edge AI compute under the optimized thermal constraints developed in TwinGrid. This deployment provides the live orbital telemetry required to validate the software-defined optimization model. The success of the first orbital node establishes the first physical asset in a growing standardized network. Deploying dual-use technology at scale requires strict adherence to international regulatory frameworks. GSS is aligned with the European Space Agency and Horizon Europe to ensure the architecture meets sovereign compliance standards. The mathematical invariants embedded in the ISS serve as a technical safeguard, preventing the physical system from deviating into unstable thermal states. This safety profile simplifies the regulatory approval process for commercial and defense missions. By integrating these compliance layers into the core architecture, ScrollCiv minimizes the risk of regulatory blockades during global expansion. The launch of the initial node cluster establishes the foundation for a distributed orbital lattice, expanding into a network of thousands of nodes. This provides a distributed backbone for energy and computation in low Earth orbit. The architecture is designed to scale beyond the orbital environment. The next phase involves the lunar expansion layer, utilizing in-situ resource utilization to build infrastructure outside of Earth's gravity well. By integrating these orbital and lunar nodes, the system creates a recursively expanding architecture. This unified fabric is designed to support the energy and compute requirements of a multi-planetary economy. The current capital round funds the transition from software validation to the deployment of the first 3-node clusters. It provides the resources to establish the physical baseline for a standardized orbital network.